So in the last presentation, I have tried to cover the basic concepts of Verilog used in digital circuit design. Now this is going to be an extra session to Lab 1, where I'd like to run some of the codes given in your lab sheet and sort of give you an overall idea about how to write, compile, and test Verilog codes using the Quartus 2 software. So I already have the software opened up in my PC. Now the first step to begin any design is to open a new project. So I just click on File, choose new project wizard, and this is where you will be able to set up your project. So click next. Here you have to set a working directory for this project. So let me choose a suitable project directory. Okay, now I have to give a name to this project. So let me type in the name. So notice that as I type in the name of this project, the field below is automatically being filled up. Actually, this is the name of the top level design entity of your project. Make sure that you give these two the same name or the Verilog compiler might show error. Alright, so click next. Next. This page, you can select the device on which you want to run your codes on the practical hardware. Since we're not going to run any code in hardware in this course, so I'm just going to leave this page as it is. So click next. Now, if you are going to use the software for the first time, this page, this EDA tool settings page, might not look the same as here, as shown here. Make sure that it looks the same. You have the correct tool name and format selected for all these three boxes: the design, entry or synthesis, simulation, timing analysis. All boxes should have the tools and formats set up like shown here. So click on next, and this page will summarize your choice during your project setup. So I'm just going to click finish, and my project is set up and ready to run. Now inside this project, I will create a new Verilog HDL file where I will be able to write the codes. So click on File, New, select Verilog HDL file, hit OK, and editor window will pop up. Now here I'm going to write some codes. So I'll just copy the code from example 1 of your lab sheet to this editor and run the code. So let me just correct some formatting issues. Alright, so the formatting is corrected, and at this point you have to save this file. So select Ctrl+S and make sure that you give the file name the same name as your module. So I'm just going to click save. Now you have to compile this code. So I'm just going to click this button which says start compilation, and the compilation is started. Now, this might take a few moments depending on your device. So please wait with patience. So as you can see, the compilation is done and I do not have any error in the code. So I can just move on to the testing phase to verify the functionality of the code. So I need to open a vector waveform file where I can observe the timing diagrams of the inputs and outputs. Alright, so now let's bring the new file window, Control N, and select vector waveform file, click OK, and the file will be opened. Now if I right click here, this portion, I will see the options for inserting the input and output nets into this file. So I will select the insert node or bus option. Here click on the node finder. Make sure that you have selected the pins all options in this filter box. Click on list and you will be able to see all the input and output pins on the top level design here. Now, if you click on this button, all of the pins will be copied here. Hit OK, again OK, and the pins appears in your waveform file. So now we need to assign values to the inputs manually so that we can check the value of the output based on the input values. To assign value to any of the inputs, simply right click on it, right click on X1, click on value, and from this drop down menu you can assign any value to your pins. Here I am selecting the clock option, and this window pops up immediately. Here I can choose the time period of the clock, so I'm just going to leave it as it is at 10 nanoseconds. Now the reason for choosing the clock option is simple, because you can get this periodically alternating values between 0 and 1, and you can simulate all possible values for the input. Similarly, I have to assign clocks to the remaining inputs as well. Now I will choose to assign a 20 nanosecond clock to X2 and 40 nanosecond time period clock to X3. Let me quickly assign these values. So now we need to assign values to the inputs manually so that we can check the value of the output based on the input values. To assign value to any of the inputs, simply right click on it, right click on X1, click on value, and from this drop down menu you can assign any value to your pins. Here I am selecting the clock option, and this window pops up immediately. Here I can choose the time period of the clock, so I'm just going to leave it as it is at 10 nanoseconds. Now the reason for choosing the clock option is simple, because you can get this periodically alternating values between 0 and 1, and you can simulate all possible values for the input. Similarly, I have to assign clocks to the remaining inputs as well. Now I will choose to assign a 20 nanosecond clock to X2 and 40 nanosecond time period clock to X3. Let me quickly assign these values. Right, so I'm done assigning the values. Now, the choice of such clock periods is easily understandable from the truth table. We observe carefully in this truth table, you can see that X1 changes alternatively at each half cycle of the clock period, whereas the changing frequency of X2 is half of X1, and the changing frequency of X3 is half of X2. So, uh, so that is why the time period of the clock of X2 should be twice X1, and the clock period of X3 should be twice of X2. So if we choose the clock periods like this, we will be able to simulate all these 8 possible case of evaluations and cross-check our output value from the Quartus 2 software with the ones shown here. All right. So now that we are done assigning the input values, let's save this file with the same name as the Verilog files. Yes, click save. So observe that the file name is already here. Just you have to save the file. Now from the menu bar, click on assignments. So before going into the assignment option, I'd like to show one more thing. From the edit option, you can choose the end time. I'm just going to choose 120 nanosecond. So click OK. And if you click here and select Control and press Control plus W, so the entire simulation time will be fitted onto your simulation screen. And here you could also choose your grid size. So this is the grid size option. So I can see that it is chosen to be 10 nanosecond, and it is also visible in your vector waveform file screen. So you can see that after 10 nanosecond, you have each grid. It's 40 nanosecond, 50 nanosecond, 60 nanosecond. So 10 nanosecond grids here. So I'm just going to leave it as it is. It's okay. Now from the processing menu, click on generate functional simulation netlist. So this window pops up because I just changed some options in the vector waveform file and I didn't save it. So just hit yes and the changes will be saved. And the functional simulation is being generated and it is done. So after the functional simulation netlist generation is successful, you can again click on processing, select start simulation, and your simulation will be started. So here we can cross-check the value of f with our truth table and verify whether our code was correct or not. Actually, one thing I missed, that here the simulation mode is selected to timing, but I actually need to set the simulation mode to be functional. So for that, I will choose the assignments settings, and from here the simulator settings, I have to choose the simulation mode to be functional. So as you can see, if the simulation mode is timing, you will be able to see the unnecessary delays for which the output waveform might not exactly match with the ones shown here in the truth table. So you have to select the functional simulation mode before simulating your waveforms, and you will be able to just cross-check your F instantly with the truth table. So click OK. So as I change the simulation mode, I will have to again simulate these waveforms. So for that, from this processing, I have to select generate functional simulation netlist. And the functional simulation netlist generation was successful. So again, from the processing menu, start simulation. And the simulator was successful, and you can really see the output values. So observe that the output time diagram is different from before. So I'm just going to fit all these waveforms to the screen. So I will again click Ctrl plus W. So here you can easily verify this F with your truth table, and you'll be able to cross check with your truth table to make sure that your code is okay. So again, make sure that your simulation mode is set to be functional. Otherwise, that if the simulation mode was selected to be timing, you will not be able to verify the output diagram with the output of your truth table. Right, so this is how you can write and compile your Verilog codes. Now, one thing I'd like to add here is that you can also see the synthesized circuit from the Quartus 2 software. So for that, I'm going to select Tools, Netlist Viewers. From Netlist Viewer, I'm going to choose RTL Viewer. So the synthesized circuit pops in screen, and you can just cross-check this circuit, the one given in your lab sheet. So this is another way to check the validity of your Verilog code, and it comes quite handy when there are sub-circuits inside the Verilog code. Now we have such a code in our lab sheet. So here, the code where we have to design a 4-bit full adder module using the 1-bit full adder block as sub-circuit. So I have this project already created in my Quartus 2 software. So I'm just going to open this project. So File, Open Project. and I'm going to choose the suitable directory. So here I created this project, and this is my project file. I'm just going to open it, double click on it, and the project will be opened. Now, this is a good way to modify your previously created projects. So in the Files tab, you can access your previous Verilog or vector waveform files. If I double click on the Verilog files, the editor will be opened with the Verilog code, and here I can modify my code if needed. I don't want to change anything here, so I'm just going to compile this code. So I can click on this button which says start compilation, or I can use the keyboard shortcut Ctrl plus L. Now the compilation has started. Right, so the compilation is done. Now I can check the timing diagrams of the inputs and outputs. So for that, I will have to create the Verilog, the vector waveform file. Now, as I mentioned, my vector waveform file was already created. So I'm just going to double click it, and the vector wave, my previously created VWF file will be opened. So here you can see I have already assigned the values to the input ports. So I don't need to assign here again. So I can just start my simulation. So as before starting your simulation, you have to make sure that your simulation mode is set to be functional. So for that, you have to select assignments, settings, and under the simulation settings, choose the simulation mode to be functional. All right, so here it is already set to be functional. Click OK. Now from processing, generate functional simulation netlist. So the functional simulation netlist is generated successfully. Click OK. Again, from the processing menu, you have to select Start Simulation, or you could use the keyboard shortcut Ctrl plus I as given here. So the simulator is successful and the simulated waveforms show up on the screen. So here you can easily verify the sum bits and the output carry bit with your own test result and check the validity of your code. Now, if I go to the RTL viewer again, Tools, Netlist Viewers, RTL viewer. So the synthesized circuit appears on the screen. So here I can see the sub-circuit box. If I just double click on it, I see that this sub-circuit is nothing but the 1-bit full adder. So there is the 1-bit sum output, and there is the 1-bit out. Alright, so as we saw in the code, this was the full add block, and this circuit was synthesized here. So this is the synthesized output of the full add block, and the main code on the top level design entity, that is full add 4. So here we can see that we have used 4 instances of the full add sub-circuit block. So here we can also see those 4 instances in the RTL viewer. So stage 0, 1, 2, 3. So these are the 4 stages of the 4-bit data block, and our synthesized circuit corresponds to our desired 4-bit full adder circuit. So this is how our validity of the Verilog code is checked. So in the end, I'd like to encourage you to simulate all the examples and class problems mentioned in your lab sheet in Quartus by yourself, because the more you practice, the sooner you will be able to get used to programming in Verilog. Thank you.